All right, in this next section, we're going to talk about the factors that affect Bronsted-Lowry acid strength. So it turns out that it's the stability of the conjugate base that we're going to be looking at, and it's a great guide to acid strength. So remember, if we have that generic acid-base reaction, in this case with water, we would form H3O plus A minus. So we're going to be looking at what are the things that make this more stable. You can imagine if it's very stable, then we're more likely to lose this H. Right? If it's not tightly held onto, for example, or if A minus is very kind of quote-unquote happy with its charge, then we're more likely to lose the H, and that makes us more acidic. So down here below, those factors which help stabilize that conjugate base and hold on to that increased electron density will in fact make it more stable, and that net result increases the acidity of our related acid. Now there's a handful of things that affect the stability of our conjugate base. One of the things that we're going to be talking about is some of those factors, and we also need to remember that later on in chemistry we're going to be talking about base strength. And to understand base strength, we'll look at acids. We'll look at the acid from which it came from. Now, the first thing that I want to look at with you guys here is the size of the atom. So we're going to go down the column. So it turns out as we go down a column of our, right, here's our periodic table column for our halogens. As we go down, our size is going to increase. And as our size increases, we increase the spread of electron density. Right? We have more electrons. And this increases the stability of our anion. And sometimes we actually say we use this term polarizable or softer. So down here at the bottom, we have a higher polarizability. And we are what we might call soft down here below. So we increased our softness, and we have a more polarizable atom. Up here at the top, we call these hard, and they're less polarizable. And as the trend kind of matches this, right, if we look down here below, iodide, which has a minus charge, right, it comes from HA. If we're losing a proton, it's coming over that direction. That's the most stable because that electron that it gained to become a negatively charged anion is more stable in an electron cloud that's farther from the nucleus, essentially. And we can see that reflected in our pKa's. So if we look over here on the side, here is a list of our pKa's. HA, right down here below with HI, our HI, that has a pK of negative 10. Right, our next HA, which is HBr, is negative 8, coming down to negative 7, and then a positive 3.2. So it's a big difference. Negative 10 to a positive 3.2 it's the difference of the pKa's raised to 10. So in essence, it's 10 to the 13 times more acidic, HI, than HF. Now, when we're talking about our conjugate base here, and we're looking at the periodic table, there's two things to consider. So I want to point out that when we talk about the size of an atom, we're looking at what happens when we go down a column. So it turns out that electronegativity affects us too. But as we go down the column, size predominates as one of our directing forces here. So it's true electronegativity changes, it goes down, but it's not as big of an effect as size is when we go down a column on the periodic table. Now, as we go across, the size changes, but it doesn't change as much as the factor of electronegativity influences what our pKa's are. Right, so if we look at this next little statement here, it's fairly straightforward to understand. And again, just kind of make a note, we're talking about across a row here. Now, the more polar the bond, larger dipole, the easier it is to pull that polarized H off its bonded atom. Right? And in addition to that, that resultant anion can accommodate the negative charge better if it's more electronegative. Right, so remember our trend in electronegativity. Up here at the top, this is a high electronegativity. Down here at the bottom, this is a low electronegativity. Right, so as we go up and over, we increase in our electronegativity. So if we look at our trend here, we have carbon, right, nitrogen, oxygen, fluorine. This is across our row here. And the stability here of these anions is fluoride is more stable than hydroxide, more stable than amide, and more stable than this carb anion. And that's because fluoride here, because it's more electronegative, can accommodate that negative charge better than an oxygen atom or a nitrogen or a carbon. And that trend is going to be true also when we look at acidity strength or acid strength. So HF is going to be the most acidic, and HCH3, aka CH4, will be the least acidic, right? So this has a pK of about 50, and over here we're about 3.2, right? This is about 16. NH3 turns out to be right around 36. Right, so remember, don't get those two things confused. As we go across, electronegativity predominates, and as we go down, size predominates. So as we go down, we're looking at size here. So down, size predominates. Okay. Now let's take a look at hybridization. We talked about hybridization before. It's something that we looked at, and remember that we have, generally speaking, sp3, sp2, and sp. Those are the most common that we see in organic chemistry. Now, when we look at something like an alkane down here below, we know the hybridization here, right? Kind of putting this in. Here's our H. We're looking at this bond right here. Right, so here's our sp3 orbital. And while we're at it, let's go ahead and put in the H atom right here. So there's your H. So we know that's sp3 hybridized. And the percent S character, this is pretty easy to figure out. So we have a total of 4 orbitals, right? S plus a P plus a P plus a P. Remember, that's how we add them together to get sp3. So one of those is S. So we have an S divided by an S plus a P plus a P plus a P, which is 1 over 4, which is 25%. Right, now the pK of that is around 50. Now if we come down here and look at an alkene, so here's an alkane, here's an alkene, and we'll talk about those at the end of the chapter. We're going to look at this bond right now, and we're going to put our H on this, so kind of ran out of space here, but we'll put our H right up there. And then that bond here is an sp2. Right, and what's the percent here? Well, it's S plus P plus P. That's how we get 3 sp2s. S is one of them, so S divided by S plus a P plus a P. So that's 1 orbital divided by 3, or that's 33%. Now, the pK of this is about 44. And part of that has to do with the fact that that bond length is shorter, so it pulls on the electrons a little bit more tighter. And that makes the H more easily, I guess, abstracted or taken off. So looking at this last one, here we have an alkyne. So we're going to be looking at this bond right here. Alkyne is sp hybridized, and again, there's our H atom. So this has 2 orbitals. I think you can figure this one out. Now it's 1 divided by 2, right? Or that becomes 50%. And the pKa of this is 25. And again, it doesn't mean it's 25 times. If we look at this difference, it's not 25 times more acidic, it's 10 to the 25 times more acidic, really. So that's a big chunk of change there. So this is a good trend to remember, that an increase in S character increases acidity. So it just helps us not have to memorize so much. And again, kind of the idea here is that the S orbital is closer to the nucleus than the P orbitals. right? And therefore, an increase in that S character brings those electrons closer, essentially, to the positive charge of the nucleus when we were talking about the carbon there. That helps stabilize the electrons, right? So the positive charge is where the protons are there. All right, guys, so let's take a look down below here at resonance. Now, we spent time talking about this before, and let's look at it. So here's a reaction between ethanol and water. So let's take a look at what happens if water were to come over and physically grab a hold of one of these H atoms. Now, don't stress too much about these arrows right now. They're introduced in more detail as we get going more through organic chemistry. But as it takes that hydrogen atom, the electrons that are here are going to come over and then reside on oxygen. So again, the big deal here is that you guys know that it's H3O plus that forms, and that we know what our conjugate base is, which is CH3, CH2O minus there. All right. Now, as I've written down here, this has a pKa of 15.9, so you could look that up in your table. And if we look down here below, here's a reaction, and this is acetic acid with water. So same type of flow. We're going to take these electrons, and we're going to swing over here if we're kind of practicing just drawing those in. It grabs a hold of that H, and then these electrons here are going to come over and they reside then on this oxygen atom. Now what that's going to give us is, same thing, we get H3O plus here, right? But now we get CH3, carbonyl, and oxygen with a minus charge. And when you look at this anion here, this is our conjugate base, this thing has resonance. So resonance is going to help kind of bear the burden of that negative charge oxygen. So this is how we would put our arrows in for electron flow here. Remember, our skeleton doesn't change. So you got your oxygen down here, and then your bonding set of electrons in that top carbon double bond oxygen become lone pair, and we get a negative charge there. And there we have it. So again, the delocalization of those electrons helps stabilize the conjugate base. And that can be seen when we look at the pKa's, right? We're going essentially from 16 down to 5. So quite a bit more acidic simply because of resonance. And note also here that, right, it's oxygen has a negative charge in both of these structures. So the only thing that's changing is the electron delocalization, or where we're putting our electron density there. Now in this fifth one, it turns out that there's an inductive effect, or an inductive withdrawing group effect. Now what the result is that more electronegative atoms on an acid, especially like if we look at this trend of carboxylic acids here, they help stabilize the conjugate base more than weaker electron withdrawers do. So if we look at this molecule, we're going from a carboxylic acid here, right? And what this does is, we've seen this before, when it loses an H, it becomes acetate, right? And then we have that resonance structure there too. Now it's that negative charge that is going to dictate whether or not we're either a stronger or a weaker acid, right? The ability to, I guess, accommodate it is what we're talking about. So they all have the resonance structure that we talked about before. So we're all going to get this happening with all four of the acids that are down below. Right, our minus charge right down there. So that's not going to change. What changes across this, though, is the number of chlorine atoms. And as we put more electron, I guess, withdrawing groups, like chlorine or fluorine on here, it helps pull electron density away from the end of that molecule where that negative charge is, right? This negative charge area here, and it helps stabilize that negative charge. So you can see the trend as we go from, right, 1 chlorine here to 2 chlorines to 3 chlorines, that our pKa goes down, and that parallels acid strength. So more halogens, we are more acidic there. Now, again, that's those halogens are not bound directly to the atom that's being lost. So we're not looking at HCl, right? We're looking at H connected to a carbon connected to something else down here. So don't get this rule mixed up with size, for example. Right? When we talk about size, that's something different because we're looking at an H atom connected to a halogen. We're here, when we talk about halogens, we're specifically looking at their inductive withdrawing effect. And the last one here is really pretty straightforward. It's something that we don't often think about, but we understand. And that is that a positive charge on an acid. So if an acid starts with a positive charge, then the loss of that proton creates a conjugate base which is neutral. And that's usually a very stable conjugate base compared to something that has a negative charge. This can be seen in this little table down below. So when we look down here below, we've got water. When water loses a proton, right, as an acid, it becomes OH minus. Okay, and that thing has a negative charge on it. Hydroxide has a negative charge. Now, if we start off with a positive charge on our acid, H3O plus, this has a pK of negative 1.7. That's a strong acid territory. When we lose that H, we become H2O, which is neutral. And that's a good thing. It's a stable thing because we don't have to stabilize a negative charge there because we already are neutral. There's nothing to stabilize.